It's funny. Have you ever actually stopped to think about your printer? I mean, really think about it. Because deep inside that machine, there's this tiny, perfectly controlled drama playing out thousands of times a second, the creation of one single, perfect drop of ink. So let's dive into the incredible science behind that. And that's the big question, isn't it? How on earth does a machine create one perfect little drop of liquid right on command? It sounds so simple, but controlling a fluid with that kind of precision is a massive scientific puzzle. Today, we're going to unpack a super cool research paper from 1994 that basically cracked the code. Okay, so take a look at this. This illustration from the paper shows the whole setup in its most basic form. You've got a continuous stream of liquid, the jet, just flowing from a nozzle. And then you have this electrode that zaps it with a carefully timed pulse of electricity. That tiny little jolt, that's the secret to everything. So let's set the stage. We're talking the early 90s, and researchers were wrestling with this really fundamental problem in fluid dynamics. But it wasn't just theoretical. It had huge practical applications for tech like, you guessed it, inkjet printers. Here's the heart of the problem. A jet of liquid, if you just leave it alone, wants to flow. It's a continuous stream. But for a printer to work, you need to be able to tell that stream, hey, give me one drop, right now. The real challenge was figuring out how to give that command and make the liquid obey perfectly every single time. All right, so when you have a big, complex problem like this, where do you start? Well, often you start by creating a simplified model, a theory that tries to predict what's going to happen. And their first go at it was this really elegant, simple idea they called the pinch model. It's really a two-step dance. First, that quick zap of electricity acts like a pair of invisible electric tweezers. It creates this tiny little squeeze or a perturbation on the jet. And then physics just takes over. The natural forces inside the liquid, these things called capillary forces, they grab onto that little pinch. They make it bigger and bigger until, snap, a drop just breaks right off. And the math behind this idea is what the scientists called their linear model. Now, you got to understand, this model was built for one job and one job only, to predict the timing. It wasn't trying to figure out the drop's shape or how big it was. Nope, just the exact moment, the when it would break away. And you know what? It seemed to work pretty darn well. This quote from the researchers themselves says their simple model was giving them rather accurate estimates. So it looked like a really promising start. But of course, in science, you can't just trust the math. You've got to test it. So it was time to leave the perfect world of equations and get their hands dirty. The researchers had to actually build a machine to see if what the model predicted would actually happen in real life. So to test their theory, this is what they built in the lab. It's basically a big, scaled-up version of an inkjet, so they could actually see what was going on. They used a special glycerin water mix as their ink. They used an electrode to apply the voltage, and this is the cool part. They used super high-speed photography to capture the action, freezing the exact millisecond that the drop broke free. And this set up the ultimate test. They had a number predicted by their theory, and now they had a real number measured by their experiment. The goal was super simple. Do the numbers match up? Is the measured breakup time, what they call TB, the same as what the linear model said it would be? And this is where our little science detective story gets a plot twist. Because as the data started rolling in, it became pretty clear that while their simple model was good, it wasn't the whole story. Here's the thing. The model was great at the when. The timing it predicted was pretty close to what they saw, but it completely failed to predict the what. Like, what did the drop actually look like when it broke off? Was it a perfect little sphere? Did it have a long tail? Did it create a bunch of smaller, messy satellite drops? The simple linear model had zero answers for that. So to solve this mystery, they had to bring in the big guns. Enter the nonlinear model. This thing was a mathematical beast. It was designed to tackle the incredibly complex physics of the liquid stretching and thinning and deforming right at that crazy moment of breakup. And its goal was very specific: predict the final shape. So you can kind of think of it like this, right? The linear model is like a stopwatch. It's a quick, simple tool that tells you when something is going to happen. The nonlinear model, on the other hand, is like a high-definition camera. It's way more complex, way more detailed, and it tells you exactly what it's going to look like when it does. Two different tools for two parts of the same job. All right, now for the main event. We've got the real-world experimental data. That's our ground truth. And we've got our two competing theories, the simple linear model and the complex nonlinear one.
It is time for the showdown.
Okay, let's look closely at this chart from the paper. See the dots and triangles? That's the real stuff, the actual measurements from the lab. The solid and dashed lines, those are the predictions from the two models. And the name of the game is to get your line to lay right on top of those dots. And, as the researchers point out, both models actually did a pretty good job of predicting the general pattern. You see how the data goes up and down kind of in waves? Both lines capture that basic rhythm, which means they were definitely on the right track with the physics. But, hang on a second. Take a closer look. They're not a perfect match, are they? There's a noticeable gap between the theoretical lines and the real-world dots. So what gives? In science, figuring out these little discrepancies is where the magic happens. And the paper gives us a huge clue. The models were based on a perfect, idealized liquid, one with no internal friction, what a physicist would call an inviscid fluid. But the real stuff they used, the glycerine-water mix, it had viscosity. It was a little bit thick, a little bit syrupy. And that real-world messiness is a big part of why the numbers don't line up perfectly. But then you get to this, and this right here is the aha moment. This is the verdict on the drop shape. On the left, you see the shape predicted by the complex nonlinear computer model. And on the right, that's the actual high-speed photograph from the lab. I mean, come on! The match is absolutely stunning. It perfectly predicted the main drop, the long tail, and even the tiny little satellite drops that broke off. Incredible. And that was the smoking gun. This was the proof. The simple model could get you close on the timing, sure. But if you wanted to truly understand and predict the shape, which is everything when it comes to high-quality printing, you absolutely had to have the power of that complex, nonlinear model. So, okay, a great science story, but why are we digging up a paper from 1994? Well, because the lessons here about how science really works and the kind of technology it creates are more relevant today than ever. The big takeaway for me is all about the power of scientific modeling. It shows us that we need both kinds of tools. We need simple models to get us quick, valuable estimates, and we need complex models when we need deep, highly accurate predictions. And mastering this kind of physics isn't just for printers. The paper itself mentions that this same technique can be used for amazing things like sorting individual biological cells. And that just leaves us with a final thought to chew on. If scientists were pulling off this level of microscopic control over liquids way back in 1994, it really makes you wonder, doesn't it? What seemingly impossible physical processes are we learning to command and control right now, using this very same combination of theory, experiment, and sheer curiosity?